Plunian, and I am coming from Grenoble. The goal of my visit here is to set up some collaboration with Dr. Raoul Avalos, Zuniga, on the project of Dynamo disk. The goal of my presentation is to give some ideas, some concept of how a magnetic field can be generated by what we call the dynamo effect, and which is occurring in the core of the Earth, and also, for example, in the convection zone of the Sun.
Dr. Franck Plunian.
In the 16th century, William Gilbert was maybe the first person to realize that the magnetic field of the Earth was a dipole. Okay, so at that time we knew they were using compass to have the direction, but he was maybe the first to understand that the magnetic field lines were like this outside the Earth, and then his idea was maybe there was a magnet inside the Earth, so a magnet like this with a north pole which is in the south pole of the Earth, such that the magnetic field line would go that way. Okay, and this idea stood for several centuries until Pierre Curie realized, so in the 19th century, that above a certain temperature, the magnet lose their magnetization. This comes from the spin of electrons. If the temperature is below some Curie temperature, then the spins are all aligned, and in this case the magnet acts as a magnet. But for a higher temperature, then it loses its magnetization. And we know that in the Earth, the temperature are much higher than the Curie point of any material. So here, this is today. This is 1 million years before, 2 million, 3 million years before. And in black, it is the polarity that we have today. And in white, it is the polarity which is reversed compared as today. And you see that along time, the magnetic field has reversed several times, many times, and not in a regular way. The dynamics are what we call chaotic. They revert in a completely irregular way. And the last time it reversed was 700,000 years ago. Thanks to the seismologist, we know the composition of the inside of the Earth. We know that there is a liquid core, about 3,000 kilometers of radius, which contains almost iron, liquid iron, and inside there is a solid core, solid inner core, and this solid inner core grows in time and releases some heat, which makes motion in the liquid core. And this is this motion, and which creates some electric currents, which makes the magnetic field of the Earth. And it is a good thing that we have such a magnetic field on Earth, because it protects us against the cosmic particles, in particular the ones which come from the Sun. So on the left, this is the Sun. The Sun releases always some particles, because there is a strong magnetic field which is also generated on the Sun. And these particles come to the Earth, and because of our magnetic field, the particles are just deviated. And so the magnetic field of the Earth acts like a shield against the particle coming from the Sun. So here you have what we call a solar flare, or a solar eruption, and it is in fact related to a magnetic field which is large scale and inside the convection zone of the Sun. So what we understand is that there are some loops of magnetic field at the bottom of the convection zone of the Sun, and sometimes these loops just go away. So they can close, like here, or they can open and then go in all the solar system. Just to give you an idea, the size of the Earth is really like the red point, so very small compared to such a big arch. In addition, the Sun, contrary to the Earth, has a magnetic activity which is regular, pretty regular. This is visible when you analyze the sunspots at the surface of the Sun. So, for example, here the white point. So this corresponds to a picture of the surface of the Sun taken each year. And you see that year after year, the number of sunspots becomes less and less, until some year where it is a minimum of a magnetic activity, and then it starts again. Here, the sunspots at some latitudes comes again. And so this is so in this graph, the number of sunspots are plotted in time. And the first people who started to count the number of sunspots, the first one was Galileo. He saw in the beginning of 17th century. And you see that, and then we got more and more precise records of sunspots. And you see that there is a cycle, quasi-periodic. So one peak lasts 11 years, but in fact, looking at magnetograms, we realized that the magnetic field of the Sun was also reversing every 11 years. So the period is 22 years. We have two objects, the Earth on the left, the Sun on the right, with a magnetic field for the Earth which is about 0.5 Gauss. For the Sun, it is between 1 Gauss and 4,000 Gauss, with some different dynamics. The reversals are chaotic in the case of the Earth. They are quasi-periodic in the case of the Sun. And both objects contain some liquid which is electrically conducting. So liquid iron for the Earth and some plasma for the Sun. So we feel that maybe there is some common mechanisms which can explain the generation of the magnetic field. And so how does it work? To understand how it works, I will first start with a simple object that everybody knows, which is that we call a dynamo, bicycle dynamo. So it is composed of a rotating part here, so which is represented here. And this rotating part is attached to a magnet. And so the magnet rotates, okay? And on the side there are some coils, which are represented here. And you know that if a magnetic field enters and if the flux changes in time, then it generates, because of the Faraday's law, an electric current in the coil, okay? And this electric current will enlight your light of your bicycle. Now, what you can do is replace the magnet by a bobina and link this bobina to this circuit. So instead of enlightening your light, you just attach it like this. Okay? So this one is rotating. So suppose that there is a small electric current. It will generate a magnetic field here. This magnetic field will generate a current in this coil, and again this current will generate a magnetic field here. And so we understand like this that if you turn sufficiently rapidly, you will have a generation of magnetic field. And this was first presented by Siemens at the end of the 19th century. Another illustration of this phenomenon, which is maybe more easy to understand, is the Bullard disk dynamo. So consider a disk in pink, which is rotating, okay? And rotating with a velocity v. Consider a wire like this, which is not rotating. Okay, so you have some contact here, electric contact, at this end and at this end. The disk is rotating, but not the wire. From Ohm's law, we know that if you have, in a magnetic field, if you have a velocity v in a magnetic field B, it will create current density J by the cross product of V and B. So here, if you suppose you have a magnetic field B, so V cross B will generate a current I like this, okay, in the disk. Then the current will go in the coil and then comes back here. And we know from Ampere's law that if there is a current in the coil, then it will generate a magnetic field. Okay, so you start from a small magnetic field, it will generate a current, and this current will amplify the original magnetic field. But the thing is that it is an instability, so you need a very small, tiny magnetic initial field in order that this works. And we can see that there are three ingredients, that I call dynamo principles, which are important for this phenomenon. The first one is to have a shear, which is here between the disk and the coil, so at this point and at this point. The second important ingredient is to have non-mirror symmetry. You see that this coil has some kind of, it is a spiral, okay? So if you look at it in a mirror, if this spiral is right-handed, in the mirror it will be left-handed. So it is non-mirror symmetric. This is what we call non-mirror symmetric. And this is necessary for having dynamo. If you would have a complete coil, then nothing would happen. And it works only if the velocity of the rotation of the disk is sufficiently large. If it is too small, it doesn't work. In particular, it must be larger than the resistance of the circuit divided by the mutual inductance between the loop and the disk. We will see during all my talk that these three principles will always come back. In all the examples I will give, even for natural objects, but also for experiments, we will always find that there is some shear, there is some non-mirror symmetry, and there is some threshold for the velocity. Another thing concerning this dynamo is that if you reverse the sign of the magnetic field, and apply exactly the same rules than before, mainly that if you have V cross B, so V cross B, it will create a current which will go in the other direction. This current then will go in this direction, and then it will generate, it will amplify again this magnetic field. So in fact, if the magnetic field B is a solution of this dynamo, then minus B is also a solution. And this without changing the sign of the velocity. So why is it important? You remember that in the case of the Earth or the Sun, you can have reversals of the magnetic field. It is the same here. If B is a solution, then minus B can be also a solution. And if you solve the equation of this problem, of this dynamo, then, so here, if you plot, for example, the vertical component of the magnetic field, then you find that indeed you have some reversals from one polarity, positive, to the other polarity, negative. Positive, negative, and so on. And the dynamics of these reversals are chaotic, like in the Earth's core. This is visible for those who are familiar with the theory of chaos. This is visible in this diagram that we call diagram of phase, and which is a strange attractor. So it means that the solution oscillates between two states, positive and negative, without never really reaching it. Start with the Riga dynamo experiment. So the Riga dynamo experiment is composed of a propeller which gives the helical geometry to the liquid sodium flow. So here you have a flow which is helical, so it has a component in the vertical direction plus a rotation. So we call such flow a helical flow, so we speak of helicity. And then the flow reverse back. And this is liquid sodium at rest. So as I said before, we have some shear. The shear, for example, between this part and this part. And here you have a vertical to the bottom and here to the top. And we have non-mirror symmetry, which is given by the helicity of the flow. For the Karlsruhe dynamo experiment, so it is composed of helical also parts, helical cells, as in Riga, but they are smaller. They are this size. The overall experiment is maybe 2 meters of diameter and 1 meter of height. And there are 52 of these cells. And so, as before, the helicity ensures non-mirror symmetry and the shear. So from one cell to the other, there is a strong shear. So again, they found some dynamo action for typical velocity in each cell, which is about 1 meter per second. And so, for example, here you see that the magnetic energy, the magnetic field grows and then saturates to some value. There is a balance in the saturated phase between the flow and the magnetic field because of the Lorentz forces. During my PhD thesis, I applied these principles to study if a dynamo action could occur in the core of a fast breeder reactor. The reason for that is that in the 90s, they observed some problems with the fast breeder reactor Phoenix. We had two in France, Phoenix and Super Phoenix. And in Phoenix, they observed some vibration, and suddenly the system of control just stopped the nuclear plant, and they didn't know where these vibrations were coming from. And so one of the possible explanation was the MHD part, the dynamo part, and then my work was to study this. So here, this is a scheme of a fast breeder reactor. So this part is what we call the primary part of the reactor, and so it has a core here. So there is a pump where the liquid sodium goes through. So the liquid sodium goes through the core. It is heated by the nuclear reaction of plutonium and uranium, and then it releases it in an exchanger, which goes then to produce electricity. The last experiment which I've been working so far is the Cadarache dynamo experiment. So it is composed of a cylinder here and two discs with plates, and the discs are rotating with an inverse direction and making a strong turbulent flow between the discs. So again, we have some shear, and the shear between the two discs. We have non-mirror symmetry because the flow is strongly helical, and they got some generation of the magnetic field, which is represented here in red. Okay, And for this experiment, we also there are difficulties to understand how it was working, because it was not working as initially predicted from the numerical calculation. And so we had the idea that maybe there was some cooperative effect, as I explained before, between the different part of the flow between the blades. So when a disk is rotating, the flow is expelled from the center to the edge. And in addition, because there are some blades, there is some rotating effect between the blades. And so, in fact, you have some helical flow, so non-mirror symmetric, and you can have some cooperative effect between these different parts of the flow. So we made some calculation about that, and indeed we find that this was enough to produce a magnetic field at the scale of the experiment. So first of all, we have been able to measure the internal rotation profile in the convection zone of the Sun using heliosysmology. So in red, it is rotating faster than in blue, meaning that the Sun doesn't rotate as a solid body, but it rotates faster at the equator and smaller at the poles. Okay? And the shear is maximum here, at the bottom of the convection zone, and here. See? So this put forward the importance again of the shear. Another mechanism which is involved in the dynamo action in the Earth's core is helical vortices. Because the Earth is a fast rotator. It rotates much faster than the Sun. If you, meaning that the Coriolis forces are much more important in the Earth than in the Sun. And the consequence of that is that the flow is organized as some helical vortices elongated in the direction of the rotation of the planet. This has been also measured in some experiments. And the effect of, if you take a single vortex, the effect is the following. If you take a magnetic field line, then it will be distorted by the vortex in such way that there is a magnetic loop which is created like this. And this magnetic loop can generate then a current density like this. So again, for that we need some non-mirror symmetry. We need some helicity. And why is it important? Because if to that you add the cooperative effect of all these vortices, then you find that if you start from a toroidal magnetic field, so like this, it is distorted by these vortices in such a way that it creates a loops. So there is some current density which is then created all along the different vortices. So a current density like this here and like this here, or in the same direction. And this current density then can generate a poloidal magnetic field. So remember, we started before from a poloidal magnetic field. Because of the shear, toroidal magnetic field can be created. And then, from this toroidal magnetic field, poloidal can be created. So the loop is closed. So, to summarize, we see that the three dynamo principles, namely the shear, non-mirror symmetry, and cooperative effect, are also effective in what we understand for the dynamo generation of the magnetic field in the Earth's core and in the Sun. Dynamo de disco that we want to build with Dr. Raoul. So why a new experiment? There have been several ones constructed so far. First of all, the experiment has been built so in some years ago, but none of them are working now. Okay, they have been exploited and then they don't work anymore. So it would be nice to have a new experiment. We believe that such dynamo disks can give some rich, different dynamic regimes, like chaotic reversals, intermittency. So intermittency means you have some magnetic field and then suddenly nothing, and then magnetic field and nothing. Okay, this is also observed in natural objects, and it will use a much smaller power than the previous experiment. Remember, 200 kilowatts. We were about 2, maybe more kilowatts. And also, if you look in details, for example, to the current lines which will be generated. So here it is difficult to see, but we will replace the coil by some spiral coils. And so the current will go from the edge to the center following a spiral direction. So this will generate a poloidal magnetic field. And as the current will flow from one disk to the disk which is below, it will also generate a toroidal magnetic field. And the main ingredients, shear, non-mirror symmetry, and cooperative effect, because we will have several arms like this, we will have them in our experiment. And what we want to also to do is to use not only one motor, but 2 motors and 2 disks with some spirals. Then, then we will play on the rotation rate of the 2 motors and probably can find some different regimes depending on the ratio of the 2 velocity of the motors. So this is our project, and thank you for your attention.
I think Raoul, it is Raoul, the leader of the project, and so I presented the main concept of the project, and hoping that this can be realized here and successful. And I also, during my talk, I also insisted on the main concept that occurs in the planets and stars, and which are also occurring in this experimental project. I discussed with several scientists in CICATA, and I think they are very good projects. For example, there is one project about the counting of bees. And so I visited some company about that, and I think it's very interesting. First visit in Mexico, so I landed in Mexico City, and I visited a few sites like Teotihuacan. To me, it is very interesting because Mexico has old history, and I like it. I was born in Paris, and so I made my high school studies in the suburb of Paris. Then after some what we call class préparatoire in France, I went in the École Centrale de Paris, and I came out as an engineer. Then I made a master in UCLA in the USA. Then I came back, made a military service. Then I worked for 1 year in a private company, and then I started my PhD thesis in Grenoble. And after a postdoc in Germany, I got my position in Grenoble. And so since then I work in the field of dynamo theory, and I became a professor in 2011.